All right, section 3-4, graphs of transformations. This is for Clayton. We are going to go through the vertical shifts, horizontal shifts, stretches and compressions. Do you guys see where these headings are?
Can we restart
Here? Nope. Vertical shift, horizontal shift, stretches and compressions. Oh, there was a reflections down here. Reflections. Those 4 things. We're going to review over those and apply them. So it's exactly what we were doing yesterday, but now we're applying them and we're graphing them a little bit, okay? So let's review up at the top, and I'm going to give you some notation that you've never seen before, but they will use like vertical shifts, okay? When you're vertically shifting something, this is the notation that they might use at some point. This is function notation. Write this off to the side. Function notation. Okay, this is the function notation that they will use. Okay, so let's say my parent function is called f of x, right? That's like a thing that we usually do. The parent function is f of x, okay? Vertical shifts mean I'm going like up, let's say up 3 or down 5. Okay, here's some examples of up 3 and down 5. Whatever your parent function is, we're calling it f of x in this case. Whatever your parent function is, to go up 3, you would do f of x plus 3. It's just tacked on to the end of that f of x, whatever the f of x is, right? Maybe the f of x is x squared, so it'd be x squared plus 3 like we did yesterday. Down 5 is just taking that f of x and you are subtracting 5, right? You're just tacking it on to the end. That's what a vertical shift will look like. Make sense? Good? So this is function notation as far as that stuff goes, okay? Let's go to example 1, and they say the graph of the absolute value of x plus 4 they want us to graph, and they also want us to graph, I'm going to do that in a different color. Let's do pink. The absolute value of x minus 3, pink. Those are the 2 functions that they want me to graph. First of all, I'm going to also graph the parent function. If I have the absolute value of x plus 4 and the absolute value of x minus 3, what's the parent? If I strip all of the numbers away.
The absolute value of x.
Just the absolute value of x. Okay, what does the absolute value of x look like? I'm putting him in black. He looks like a perfect V, right? Okay, starting at 0, 0, and he's going up 1 over 1, up 1 over 1, up 1 over 1, or up 1 over 1 to the other direction. He's at a perfect 45-degree angle, and he looks like this. Oop, come on. Like that. That is just y equals the absolute value of x. That's what he looks like, okay? Now I'm wanting to also, on that same thing, graph the absolute value of x plus 4. How does that move him?
Up 4.
This guy is up 4, okay? All right, so we're going to start now instead at a positive 4, and I'm going to go up 1 over 1, up 1 over 1, and start at 4 and go up 1 over 1, up 1 over 1, and that's what he's going to look like. This is y equals the absolute value of x plus 4, okay? The other one is the absolute value of x minus 3, and that is moving him how?
Down 3.
Down 3. Okay, so we're going to start at negative 3 instead. Go up 1 over 1, up 1 over 1, up 1 over 1. Or up 1 over 1 this way. Let's see if I get like that. And this is y equals the absolute value of x minus 3. Okay, so the same thing. They're all like those absolute value functions, just moved up and down and all that good stuff. Okay, happy with that?
Yeah.
Make sense? Good? All right. Okay, now horizontal shifts. Let's talk about the function notation for horizontal shifts. Okay, this is function notation. Okay, function notation. So let's say our parent is still called f of x. Maybe it's x squared, or maybe it's x to the 3rd power, or maybe it's the absolute value of x. But our parent is f of x, parent. Okay? When you are shifting stuff horizontally, let's say you're going 5 units left, or you're going 6 units right. Okay? What you're going to do is you're going to put that inside of the function. So then rather than f of x plus something or f of x minus something, this is what it looks like. This would be f of x plus 5, right? You would put the x plus 5 inside of the parentheses wherever the x is. You're replacing the x with the x plus 5. Does that make sense? Okay, it's like inside of whatever the function is, okay? 6 units right would be x minus 6, right? And the thing to note here is that it's the opposite symbol of what you think. Left means plus and right means minus, yeah?
Can you scroll up a little bit?
If it's in the parentheses,
then it's
Right.
horizontal, right?
Sure. Yes. Okay. Good?
No.
No?
Yeah.
Okay. All right. So we're going to graph this one. I'm going to graph this one in blue, and I'm going to graph this one in pink. But we're going to do the parent function first in black. What is the parent of that guy? What is his parent function? This is weird. Y equals? We'll just call it Y. 1 over X, right? Do you know what 1 over X looks like?
No.
If you need to use your cheat sheet, use it.
It's up there. It's a boomerang.
It's the boomerangy things, okay? Now, the boomerangy things, when you're graphing Y equals 1 over X, okay, they have vertical asymptotes at 0 and horizontal asymptotes at 0. So that's what he looks like, okay? And then the boomerangy things are just here in the first and third quadrant, like that. Oh, heavens to Betsy. I can't draw like that, something like that, okay? There are those guys. That's what he looks like. Right there and right. Let me make this one. Oh, I still can't. That's the parent. That's Y 1 over X.
Okay.
Right? Y equals 1 over X. Okay. Now, when I'm doing the 1 over X minus 3. Now, this guy is technically like in parentheses in the bottom. That's moving him how?
3 to the right.
3 to the right. Okay. Now, the beautiful thing about this thing is when you're graphing him, I would shift the asymptotes first before you graph him. So if I'm moving him 3 to the right, the horizontal asymptote is going to stay in the same spot. But the vertical asymptote is going to move over here. Do you see that? 3 to the right. This guy will stay here, and then he will just be here and here instead. Do you see that? We've shifted him over. He's now in the blue. This is Y equals 1 over X minus 3. That's what he will look like. Make sense? Makes sense. I don't know why my thing is still there. That's really annoying. Come on. Okay, then -4, that pink one, is going 4 units to the, or actually it's +4, but it's going 4 units to the left. So this is left 4. Again, your horizontal asymptote's going to stay in the same spot, but your vertical one is going to go 4 units to the left. So he'll be right
That looks crazy.
here. And then this section right here. And this section. So that's a lot of stuff to graph on one thing. But he is Y equals 1 over X plus 4. Yeah? Happy with that?
It's a
Similar to
worksheet.
similar to this. This is pretty easy. Yeah, not too bad. Okay? Happy with that? Moving on?
Yeah.
I don't know. Yes. All right, reflections. Let's do the function notation for reflections. So, function notation. Okay. If you're reflecting over the x-axis versus reflecting over the y-axis. Okay, your parent, again, we're going to start with just f of x, whatever that f of x is. And the difference between an x-axis reflection and a y-axis reflection is where you put the negative. So if it's x-axis, does the negative go inside or outside?
Inside. Outside.
Outside. So this will just become negative f of x. Versus, what will it look like for y?
Inside.
So what will it look like?
F of negative x.
F of negative x. This is like function notation, right? So if it's an absolute value, it'll be absolute value of negative x. If it's x squared, it will be negative x in parentheses squared. Okay, so look like that. Make sense? Good? That's the function notation for it. You're confused? It's just where you put the negative. Okay, so like let's say my parent function is f of x equals the absolute value of x. Okay, this guy right here says that if I'm reflecting him over the x-axis, x, he will be f of x equals negative absolute value of x. Versus on the y-axis, he will be f of x equals absolute value of negative x. He'll be in the inside. Does that make sense? That's the different types of reflections, okay? So this is just the generic way of saying whatever your function is, the negative is going to go on the outside or the inside depending on x or y, right? Does that make sense? Yeah, yeah, okay. All right, so let's go down here and let's talk about this one. I'm going to change this function though. This is the greatest integer function, those little brackety things, but we're not going to talk about greatest integers, so we're going to switch them to be just absolute values. Okay, so change those brackets to just be absolute values. We're going to graph the absolute values. You need to put this away.
I have one question left of typing, and then I'll.
You need to put your stuff away.
I can't close it otherwise.
Okay, then put it down here.
Okay, I'll turn the brightness all the way down. There you go.
We're right here. There you go. Okay. All right, absolute value. Let's graph his parent function. Parent is y equals the absolute value of x. Okay, and we've already graphed him once in this section, so here he is right there and right there. There's y equals the absolute value of x. We've already graphed him. That's the parent. Okay, then I'm going to do this one in blue, and the negative on the outside is which one again?
X.
Over x. Okay, so we're going to reflect that over x. How does that move him? He's going to go down. So he's flipping all the way down, and he's flipping all the way down. Okay, this is y equals negative absolute value of x. He's flipped down. Okay. Okay, this one is over the y-axis. Okay, and Kelsey just said, isn't that the same? Is it the same?
No.
If you take this original guy and you reflect him over the y-axis, does he flip
Yeah.
on top of
Yeah.
himself? Yeah, do you know why? The absolute value of negative x is the same thing as the absolute value of a positive x because it turns a positive, so it doesn't matter. Ah,
Whoa.
what just happened?
HDMI cord.
HDMI cord. I touched it. Shoot.
How dares practice problem?
How dare me.
Done for
There it goes. Nope, it's coming. Okay, so over the y-axis, just graph him on top of the black one. I'm going to kind of try to make it so that you can see the black one through it-ish. And there's what he looks like. So this is y equals that. Ah, come on.
And which exercise would it be? The number it is?
There we go. Oh,
Did anyone else think Breck's voice sounded like that roller coaster kid in that video? Did you think of that roller coaster kid?
I really don't know what you're talking about.
That's what I thought. Like he's getting
What is the
interviewed on like the
There we go.
Jimmy Fallon show or whatever. Jimmy Kimmel,
okay,
whatever he
next.
is.
Stretches and compressions. This is vertical and horizontal. Okay, so let's go over here. Vertical, horizontal. This is function notation. Here you go, function notation. So parent is still, we're going to call him f of x. This is function notation, so this is just the generic form. Okay, let's say we are vertically stretching by 3, and let's say we're vertically compressing by 1/4. And then let's say we are horizontally stretching by
1 something.
5 and horizontally compressing by 1/6.
Oh, okay, got it.
Okay, I'm trying to use different numbers so that we have, like, you can see what's going on. Okay. Vertical stretch, vertical compression, horizontal stretch, horizontal compression. Good?
Yep, good.
Okay, vertical stretch. If I'm stretching it by 3, how does that change my f of x?
What?
If I'm vertically stretching by 3, what is
F of
Oh.
3x.
it? Nope.
For 3.
It will become 3 f of x. That's what he will look like. I just take 3 times whatever the function was. So if it's absolute value, it's 3 absolute value of x.
Why do you
If
keep
it's
the
x squared, it's 3 x squared.
Is
Why
3
do you
absolute
put the
value
F?
that just goes up by
I'm
3?
just doing the generic one. So this is just saying, regardless of what f of x is, you take 3 times that. So it can be anything you want it to be, right? That's just the generic rule. Okay? Vertical compression by 1/4. What does that look like?
1/4.
1/4 f of x. So whatever f of x is, you just multiply 1/4 out in the front of it. Okay? All right. Horizontal stretch by 5. What's the difference there? You change it to be 1/5, but it also goes
Inside.
inside. So we're replacing the x with 1/5 x. That's what he looks like. That's a horizontal stretch by 5.
Yes.
Yeah? Okay. What about a horizontal compression by 1/6?
F of 6x.
F of 6x. The 6x goes inside of whatever function you have. So if it's an absolute value, the 6x will go inside the absolute value bars.
Oh, it's stinging.
Okay?
Why is
Oh, you're right.
Isn't a vertical stretch
Okay.
and horizontal compression the same thing?
Kind of. If it's a linear function, yes. If it is a quadratic function, like let's say I have a horizontal compression, let's say a horizontal compression by 1/2, right? Okay, and my parent function is x squared. Don't write this down. My parent function is x squared, okay? So what I would do is I would do 2x inside of parentheses, right? Okay, which actually is 4x. So a horizontal compression by 1/2 in a x squared function is the same thing as a vertical stretch by, or this should be squared, by 4.
Oh,
Right?
okay. Yeah.
So they are the same, but they're different numbers depending on what your parent function is, right? If it's a linear function, it's just the same number but flipped, right? Okay, but in a squared function, it's squared. In a cubic function, it's cubed, okay? So it won't always be exactly the same, but close to it, okay? Happy with that? Let's go to this guy. So, looking at these two right here, these are both vertical. 2x cubed and 1/4 x cubed. What's the parent?
X cubed.
Y equals x cubed. What does he look like if you graph him? Just y equals x cubed.
This. He looks like this.
Okay, so he starts at 0, and I'm going to plot some actual physical numbers here. If I take 1 and cube it, it is 1, right? If I take 2 and cube it, it is 8, okay? If I take -1 and cube it, it's -1. If I take -2 and cube it, it's -8. So this is the parent. Right? I'm going to take some actual numbers rather than just like willy-nilly graphing it on there, right? Okay, this is y equals x cubed. That's my parent function. Okay? I plotted some actual points.
Okay.
Okay? All right, moving on. Ready for that? Okay, now 2x to the third power. How does that thing move him?
Vertically stretches.
Vertical stretch by
2.
2. Okay, vertical stretch by 2. So this first point is still going to be at 0, 0, right? But when I go over to 1, rather than going up to 1, I'm going over 1 up to 2. Rather than going to 8, I'm going to 16. So it's going to be really tall like this, right? Going all the way up to 16. And then the same thing down here. He's touching at -1, -2, and going all the way down to -16. So he's going to be a lot taller than what the first one was. Does that make sense?
Yeah.
Okay. All right. This next one, 1/4 x to the third power, is a vertical stretch by, or excuse me, not a vertical stretch, a vertical compression by 1/4. Okay. So he's still going to start at 0, but rather than going over 1, up 1, he's going to go over how?
Up 1 over 4.
Up 1 over 4. He's going to be really like wide, right? Wide and short.
Oh, yeah.
Yeah, wide and short. Okay. If I would do 2.
8.
Oh, no, wait. Yeah. So 8 over this way will be at 2, like this. Like 2/8 would be at 8/2, whatever, like that. Okay, so he's going to go like this. Something of that nature, and same thing over here. Like something of that nature, really wide and like whatever. If your points aren't perfect, I'm okay with that, but just get like the first point good. Show me that like he's just a little bit wider than normal. Right? Oh, wait a second. I don't think I did that quite right. Hold on, erase him.
I can't.
You can't? Okay. Hold on. Let's do this better, I think. Over 1 would be up 1. So instead of being up 1, we're at a 4th. That's how this goes.
Oh.
Over 2 was normally at 8. What's a 4th of 8? 2. So now this is how this works. There we go. That's what he should look like. I know he was looking too wide. Yeah. So that's better. That's better. Okay. He was looking a little too wide there. Yeah. So you only go up to a 4th. The second one you go up to 2. Okay. That's better. Okay. So that is y equals 1/4 x to the third power. Okay. Happy with that? Let's do the next one. This is a horizontal compression and stretch. Okay, and I'm going to switch this. Instead of greatest integer function, we're going to make these absolute values. So let's do that. Parent is Y equals the absolute value of x, which we've already graphed like a ton of times in this section. Okay, absolute value of x is that v
I like these ones.
and the v. You like these
Then
ones?
your arrows can go like perfect with the corners.
Yeah, I know, right? It's perfect. It's so satisfying. And except when I like make your axes wrong, because then it won't be the corner. Anyway, okay. So there's that.
Stretch is gonna be skinny.
Oh, wait a second.
Yeah?
What is this guy?
He's outside.
He's outside.
Yep.
Vertical.
Wow.
So he's a vertical stretch by 2.
Right.
That's
What?
I just said.
Vertical stretch by 2. Vertical stretch by 2.
So
Okay?
he's gonna be skinny.
So he's going to be skinny. So instead of going from this center point right here, instead of going over 1, up 1, we're going to go over 1, up 2. And over 1, up 2. And over 1, up 2.
Never draw the arrows on the absolute value ones.
What?
Is that just because you just don't?
I didn't draw that. Oh, yeah, I don't know. I don't know why. Because I'm just being lazy.
Okay, sounds good.
But they should have arrows, yes, correct. I'm just lazy. That is what
Oh,
y
yeah.
equals 2 absolute value of x looks like.
You stop moving the table. I'm not.
Okay, good?
Yes.
All right, now this one. What the heck is going on here? This is a what?
Horizontal.
Horizontal compression by
2. 1/2.
1/2.
Is it a horizontal
Okay.
stretch by 2 then?
What?
Or am I just
That was a vertical stretch by 2. Vertical stretch by 2 and horizontal compression by 1/2.
This one.
Okay.
I'm saying like if it's
This one, if we start here, okay, and I'm compressing horizontally, instead of going over 1, up 1, I'm going over 1, going over 1/2, up 1.
What?
Like I'm not going as wide. I'm horizontally compressing it. He's half the distance. Anybody get this figured out?
No.
Over half up 1.
Over 1/2, up 1. Half of 2 would be over 1, up 2. Like I'm going half the distance out.
Bro, he looks the same.
You do look the same. So it's gonna be the same as
Okay, in this case, a vertical stretch by 2 and a horizontal compression by 1/2, that's doing the same thing. Yeah? Do we see
Yeah.
that?
I see it.
I'm vertically stretching him by 2. I'm making him taller, but that's making him skinnier in turn, and horizontally compressing him is the same thing as vertically stretching him, right?
Yeah.
And a lot of times that will happen. Okay? So this guy is going to look exactly the same. Y equals the absolute value of 2x. It's doing the same thing to him, right?
doing.
If you can't figure out where your points should be located, what you can do is just like plug numbers in, like plug 1 in, plug 2 in, plug 3 in, plug 4 in, right? And get those numbers and you can see what he looks like. So that's another way you can just plot the points, right? Plug the numbers into the equation. Yeah, that might be helpful for you to see if you can't get the values exactly right.
Probably.
Yeah. Okay, last couple ones. Graph the following function. Now, these are the ones where we're going to skip number 7. Example 6, this is where we have lots of stuff going on.
Origin is at
Lots of stuff going on. Okay, so how many things are happening to this function?
3.
4.
1, 2, 3,
4.
4.
4.
4.
That's what I said.
1, 2, 3, 4. There's 4 things happening. Okay, now, the 4 things are the negative, the 2, the negative 1, and the 4, but not in that order. And order does matter in which you write them out, okay? The order does matter, okay? Here's how you decide the order when you have multiple ones going on at the same time. No,
Dang it.
it's easier than that, okay? It's easier than that. When you have multiple things going on, here's the order. Are you ready?
Negative.
It's easy. If I were to plug a number in for x, I'm plugging the number in for x. Would I apply the negative, take it times 2, subtract the 1, or add the 4 first?
Take it times 2.
You would take it times 2 first, so the 2 is going to come first, okay? Multiplying him by 2 is going to do what?
Make him skinny.
It's going to be a horizontal compression
Yeah.
by 1/2, just like we just did, right?
See,
It's
I'm
inside.
doing it right.
Horizontal compression by 1/2. Okay, now, after I've applied that 2 is taken care of, would I apply the negative, subtract the 1, or add the 4?
Subtract one.
Negative.
You would subtract the 1. How does the 1 move it?
It goes
Right.
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 To the right 1. Okay,
Now
now,
negative.
that's done. Now, assuming the parent function doesn't count, right? You would take the absolute value, but the parent function, that's a part of the parent function.
No.
Would I apply the negative or add the 4?
Add the
Negative.
4.
Apply the negative.
Dang it.
Okay, how does the negative move him?
I still got the
Reflect
right
over
answer.
X.
Over x. Okay, and adding the 4 is the last thing, is up 4. Those are pretty simple
See,
rules,
I
right?
did it right before you.
Okay. All right, so our parent function, I'm going to graph him on here. He is the absolute value. He looks like this. Okay, and we just got doing a horizontal compression by 1/2, right? It's going like over 2 up 1, over 2 up 1, or excuse me, over 1 up 2, over 1 up 2. This is what he looks like. Okay, I'm just going to graph him dotted because we're going to move him.
That's right. Yeah.
Yeah?
What?
Okay, that's what the horizontal compression looks like. That's number 1. Check.
No, you're right.
That's what he looks like. Yeah? This is the horizontal compression. So the parent function, we've done a horizontal compression, right? Now, going to the right one. Okay, I move him 1 unit to the right, so now he's here. Okay, you gotta follow this. Ready?
Yeah, but I don't get
To the right one.
Because if you're putting it all together.
To the right one. Then you're flipping him down, right? So he's gonna go down like that. But then you move him up 4. Okay? All right, so to the right one, flip down, up 4. This is where he's gonna start and he's gonna go down. He goes down 1 over 1, or excuse me, down 2 over 1, down 2 over 1, down 2 over 1. This is what he's gonna look like.
I don't know.
I think it's.
Because I got the same graph as that.
Was that confusioning?
Yeah.
You have to like
Like,
do
look
4
at
things
it
at the
and
same
do
time.
it.
What?
Yeah, just look at
the
it and do
problem
it. It's
and
not
do
that
it.
hard.
You know, sure. I mean,
Like
whatever.
I'm saying,
I don't know.
I don't get the whole like vertical stretch, horizontal compression.
Me neither.
thing. Like, I would
I
rather
don't
just
know.
look at the slope and graph it as a slope.
You know, whatever. If you can do that, sure.
But then I don't know if it changes when it's like a third.
Then you gotta do it my way.
Well, I don't know how to do it like that.
Okay, does this make sense? We're going to the right one, up 4, flip down, and half as wide. Yeah? That's what's happening.
Okay.
To the right one, up 4, flip down, and skinny. Yeah?
No.
Yeah, that's what he looks like. That's all other things.
Nope. I don't.
No? Right one, up 4, flip down, and skinny. Yeah.
Rico, you hear me?
Good? Happy with that? We'll skip the last one and then that's it, right? If you need to, use your cheat sheet. Use this guy. If you don't remember what the functions are, you can either use your notes or use this guy, right? Okay, there he is. Your homework assignment is a worksheet. Do all of them. They're short, especially the first 6. Are you listening to this? The first 6 problems, all you have to do is list the parent function. You should be able to get those like lickety-split in like 30 seconds. All right? Everybody say bye, Clayton.
Bye.